Alright, hello class. In this video we're going to be talking about alternating series. And as far as tests go and series go, this might be the easiest one we have to deal with. We've already kind of looked at alternating series. Those are series that alternate between positive and negative, positive and negative. So the series here that I've written would be k going from 1 to infinity of, well, we have a 1 over k piece, right? Because we have the 1, the 1/2, the 1/3, the 1/4. And then we have, let me give myself a little more room here. And we have the alternating piece. So the negative 1 to the, in this case, it's probably k plus 1, because when k is 1, we'll get negative 1 squared times 1 over 1 plus negative 1 cubed times 1 over 2 plus negative 1 to the 4th times 1 over 3, and that does match what we have up here. This will be 1 minus 1/2 plus 1/3, then minus 1/4, etc. Okay, so alternating series tend to have, well, an alternating piece, a piece that alternates it between positive and negative. Okay, so if we have an alternating series, say A in this case, which is a series k going from 1 to infinity of negative 1 to the k plus 1 times ak, or I put here, it could be negative 1 to the k. It doesn't have to be k plus 1. Right? The starting point isn't, or how this works, whether you start with a positive or a negative, doesn't really matter that much. Okay, we want this to be a series where the terms ak, so the ak's themselves, are positive and decreasing. Okay, so of course the terms of the series in general are not positive because they're alternating between positive and negative, but what we're saying here is we want the series where the terms, when they're not alternating, are positive and decreasing. So then if AK converges to 0, then A converges. I mean, that's literally all there is to it. If the non-alternating pieces go to 0, then the alternating series will converge. Otherwise, the series diverges. Okay, so like as I promised, this is probably the simplest test we have. And this is only true for the alternating series. All we have to do is check that the non-alternating part goes to 0. Okay, to give a quick example of how this works, in this case, we have the series k going from 1 to infinity of negative 1 to the k plus 1 all over k squared. Well, our AKs, if we write it like this, okay, so our AKs are 1 over k squared. Now these are positive and decreasing, and they converge to 0. So, by the alternating series test, A converges. Right, so it's really that simple. And the reason it works that way, well, actually, maybe this next example would be better. So this maybe isn't that surprising because we know that the positive version of this, right, the series just 1 over k squared without the alternating piece, so that would be 1 plus a 4th plus a 9th plus a 16th plus a 25th. We already know that this converges. It's a convergent p-series. So all the alternating version does is this. It starts at 1, but then it subtracts the 1/4. Then it adds the 1/9, then subtracts the 1/16, adds the 1/25, subtracts the next one will be 1/36, and so on and so forth. Okay, so what ends up happening is, so this one definitely converged. It's a convergent p-series, and this one will also converge because we're actually what we're doing is, instead of adding positive values over and over and over again, we're adding and then subtracting something smaller, then adding something smaller, then subtracting something even smaller, then adding something even smaller, then subtracting something even smaller. So our terms, instead of doing this above 0, instead are doing this. Okay, so when we sum them up, we should be reaching or decreasing down to 0, or maybe not 0, but there's no way by making half of the terms negative, like subtracting them away, is going to make this jump up to infinity all of a sudden. In fact, if anything, it's going to make the sequence of partial sums converge to their value maybe even faster. Okay, where this becomes actually pretty interesting is when we look at this guy here, the series -1 to the k plus 1 times 1 over k. Well, this is the alternating series version of a divergent p-series. So this is the alternating form of the divergent p-series. (1 over k). Well, here's what's interesting. All right, the AKs in this case are 1 over k. Okay, now these are positive, they're decreasing, and they converge to 0. So by the alternating series test, B converges. And that's kind of crazy because this non-alternating version does not. So the non-alternating version does not. So what we found is that 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth, and on and on and on. This diverges, right? It does not go to 0 fast enough. But when we start alternating, so we go 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth, so on and so forth, this will actually converge. So this converges. And it turns out that this 1 over, so remember, the series 1 over k to the p diverges when p is less than or equal to 1, and converges when p is greater than 1. So 1 is that cutoff point, right? So anything greater than 1 will cause it to the series to converge. So even something like this, the series of 1 over k to the 1.0000001, that will be just enough to get it to converge. Well, similarly, if we, instead of adding every every even term, instead of adding them, we subtract every even term, then that is enough to get the series to converge. All right, this is called the harmonic series, if you've ever heard of that. This is basically the cusp of the p-series convergence. It's right on the dagger's edge, basically, right on the knife edge, where anything could possibly tip it back over into convergence, either by raising it to something really close to 1 but just slightly greater, or subtracting every other term instead of adding every other term. Okay, let's look at another example. This one, unfortunately, the series is not given to us. So we need to find a way that we could construct it. So if I think of this being k equals 1, and this k equals 2, and then this k equals 3, and then this k equals 4. Okay, and then I think of this as 2 over 1. All right. So it looks like to me that the series we have here, I'm going to start it at 1. You don't have to start at 1, but that's the first thing I thought of, and it seems to work. It looks like the denominator of the fraction is k. So first of all, we definitely have an alternator. Makes me think we're talking about a car, but we have an oscillator, I guess, is the more accurate way to say that. And it's going to be a k plus 1 because when we plug in 1, we need an even number here. And then it looks like we have a fraction where the denominator is k, and the numerator is k plus 1. So let's see if, I'm going to just check this. If I plug in those values, -1 to the k, and my k here is 1, so 1 plus 1 times 1 plus 1 over 1, then plus -1 to the 2 plus 1 times 2 plus 1 over 2, plus -1 to the 3 plus 1 times 3 plus 1 over 3. And I'm just going to check these three to see if they match. That'll be -1 squared, so that'll be 2 over 1. This will be -1 cubed, so that will be, whoops, so that'll be -3 halves, then plus 4 thirds, and yeah, that looks like what we were given. Okay, so now our AKs, or I guess in this case it would be CKs, but whatever, are the k plus 1 over k. Now, they are definitely decreasing. Okay, in fact, we can rewrite this as k over k plus 1 over k, which is 1 plus 1 over k. And so this piece will get smaller and smaller, so the whole thing's decreasing and positive. However, it does not go to 0. In fact, it converges to 1, which is not equal to 0. So, by the alternating series test, C diverges. Okay, now what ends up happening is, and this is actually one of my favorite series to talk about, eventually this series, if all the terms eventually go to 1, then eventually C mimics this series. Just -1 to the k, or k plus 1. And this series, negative k to the k plus 1, does this. It's 1 minus 1 plus 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 1, etc. So it's plus or minus 1 over and over again. Now some people might say, well, hang on, doesn't this converge? Because isn't this just, if we group these like this, isn't it just 0 plus 0 plus 0 plus 0 plus 0 plus 0, and so a bunch of zeros, so it just becomes 0? Well, unfortunately, no. Because if you were to regroup these this way, right? So group them now where you have a 1, and then if you regroup it, you'll now have 1 plus 0 plus 0 plus 0 plus 0, on and on and on. So that will be 1. Oh, that seems a little crazy, doesn't it? Well, here's what's happening. If we look, remember, a series converges if and only if the sequence of partial sums also converges. Okay, so this is what we have to fall back to. All right, so when we look at the sequence of partial sums, well, S1 will just be 1. Then S2 will be 1 minus 1, which is 0. Then S3 will be 1 minus 1 plus 1, which will be 1. And S4 is going to be 1 minus 1 plus 1 minus 1, which is 0. So what happens is the sequence of partial sums goes 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0 over and over and over again, which means we have a pattern, but there's no one number that this thing ever gets to. So this limit does not exist. So this series, -1 to the k plus 1, diverges. Now this is one of those cases where we have a divergent series that isn't actually jumping to infinity, right? It's not actually jumping to infinity. Its limit doesn't exist. It just jumps back and forth between -1, or sorry, 1 and 0. Okay. So anyway, that was a very long walk to basically describe why C is divergent. What I hope this also shows is that once infinity gets involved, okay, you cannot just reorder things and hope that it's going to work out okay. All right, sometimes you can, sometimes you can't. And we'll talk a little bit about that in just a bit later on. Okay, so for our next example, let's look at the series k going from 2 to infinity of -1 raised to the k of the natural log of k over k. All right, well, our alternating part, so our AKs are this ln k over k. Now for k greater than are equal to 2, the AKs are positive, and they should be decreasing. Okay, that's always something that we can double check if we need to. And the limit should go to 0, but let's double check that. That's an infinity over infinity, so if you don't see it right off the bat, you could use L'Hopital's rule and get that this is 1 over k over 1, which will go to 0. There we go. So by the alternating series test, D diverges. Okay, so next up, I'm going to talk about that if we take the series of absolute values of a sequence and that converges, then we say that the original series converges absolutely. However, if the series of absolute values diverges and our original series converges, then we say that this original series converges conditionally. I'll be honest though, I don't typically use this terminology very much. However, absolute convergence is very important. And what we're basically saying here is, I think it's easier to see what we're talking about if we look at an example. So let's consider the alternating version of 1 over k squared and the alternating version of 1 over k. Now both of these converge, right? A converges and B converges, and both of these are by the alternating series test. Okay, we've already looked at that. However, if we look at the series of absolute values of A, right, if we take all the absolute values, all right, then, well, first of all, every positive or negative 1 is just going to become a positive 1. And then 1 over k squared is positive, so it's just going to come out to be the series of 1 over k squared, and this is a convergent p-series. So this series converges, so A converges absolutely, right? Because its series of absolute values also converges. On the other hand, B, well, if we look at the series of absolute values for B, once again, the absolute value of the negative 1 to whatever power, that's just going to become a positive 1. And so this will become the series of 1 over k, which is a divergent p-series. So B only converges conditionally. Okay, so that's really what these definitions mean. So the checking to see if something converges absolutely is actually what's more important. Here's why. Okay, so if the series A converges absolutely, then A converges. So in other words, if the series of absolute values converge, so if this series converges, this gives us automatically that the series with, say, negative values in it also converges. Okay, so that can actually be kind of can be important if you're looking at a series and you don't want to think about the negative values. So for example, this is the example I like to think of where this is useful. Okay, so consider the series W, which is the series k going from 1 to infinity of, let's just say, sine of k over k squared. Okay, we're going to have trouble using a lot of our series tests on this particular series because of that sine k, right? The sine k oscillates. And unfortunately, I've just put a k in there, right? So it's not going to oscillate in a way that is very nice, unfortunately. So it might, so if you look at sine of 1 is like 0.8. So this is going to be like 0.84 over 1 plus then sine of 2 is 0.91 if you round over 2 plus sine of 3, which is going to be 0.14 over 3 plus then sine of 4 is, now we're down to the negative. So now it would be minus 0.76 if you round over 4, etc. Okay, so it's not a nice oscillator. So we can't just use the alternating series test because it's not alternating. It's just oddly, wildly, strangely oscillating. Okay, however, because of that, we can't use a lot of our tests. Remember, a lot of our tests say, hey, all the terms of the sequence have to be positive and like decreasing, but all of them tend to require that they be positive. So here's what we can do. Consider instead I'm going to call it W star, which will be the series k going from 1 to infinity of the absolute value of sine of k over k squared. Now, if I just look at these terms, well, absolute value of sine k over k squared, well, the denominator is always positive, so I can drop the absolute value bars here. And then the absolute value of sine, well, sine itself is trapped between -1 and 1, so its absolute value is always less than or equal to 1 over k squared. And now we can use the direct comparison test because this is completely positive. And maybe 0, but mostly, actually, no, it can't be 0 because the only way it would get to 0 is if we put a multiple pi in here, and we're never going to get a multiple pi by just putting in natural numbers. So this will always be positive. So by the direct comparison test, W star converges, which implies W converges absolutely, which means that W converges. Okay, converging absolutely, well, it's in the word. If it converges absolutely, then it definitely converges. Okay, so sometimes there are certain cases where it would actually be easier to check the absolute value series and show that it converges. And if you can show that that converges, then the original is also going to converge. Okay, so what I want to leave you with, and yeah, this ends up being a fairly short section, but what I want to leave you with is that this idea here is what we will start to use when we start putting x's in our series. Right? So I might have x's and then x over k squared or something like that. Okay, and I might be describing a function this way. This is a bit of a spoiler alert here, but what we look at instead is the absolute value. That way we don't have to worry about x's being positive or negative, right? We instead look at the absolute value of x, and we look at that series and see where it converges absolutely, and then that will tell us where the original one also converges. Okay, so I will leave you with that absolute convergence implies normal convergence, and I will catch you all on the next one. Cheers.